In this lecture, we want to learn how we can find the appropriate value for k points in quantum espresso input file. Many quantities we need to compute involve an integral over the Brillouin zone. An example is the electron density with this relation. In practice, the integral is discretized. For example, suppose we discretize the Brillouin zone to 16 points. Thus, we have 16 points, I mean 4 times 4 k points. To calculate the integral, we use the method named Monhorst and Pack. In this method, we have 3 types for k points, I mean k1, k2, and k3. We can see for k1, 4 points are equivalent. This, 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 and this. Thus, its weight is 4 over 16, or 1 quarter. Also, for K2, there are 4 equivalent points. This, 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 and this. Therefore, its weight is 4 over 16, or 1 quarter. But for K3, there are 8 equivalent points. This, 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 this. Thus, there are 8 equivalent points. Therefore, its weight is 8 over 16, or 1 half. Thus, the integral of a converts to summation of a at k1 points times its weight plus a at k2 points times its weight plus a at k3 points times its weight. To find the appropriate value for k points, we change its value in k points section in input file. These first 3 numbers means number of k points in x, y, and z direction. Also, these 3 points means k1, k2, and k3. That means offset values. To reach convergence with respect to k point, we should change the k point and then see the total energy at the output file. To do this, we create 5 different input files with different k points. For example, in this folder, you can see input file here. For example, we choose 6 times 6 times 1 for k point. In another folder, for example this, in the input file, we choose 7 times 7 times 1 for k point. And in this folder, we consider 8 times 8 times 1 for k points. Also, this folder consider 9 times 9 times 1 for k points, and this folder consider 10 times 10 1 for k points. Then, for each input file, we run self-consistent field calculation and collect the total energy. We can find the total energy at output file. For example, in this case, at output file, we can find the total energy here. Therefore, we find the total energy at output file. After that, we collect this data in a file such as k.1. In this file, there are two columns. The first columns contain k points and second columns contain total energy that is extracted from output files. By using GNU plot, we can plot this file. To do this, we open terminal environment and then we type GNU plot and then plot k point, plot k.1 with lines. From the figure, we can find that the total energy reached convergence at k point of 10 times 10. Thus, we consider k point of 10 times 10 in future calculations.